A very good afternoon to everyone. And yes, so last week I was explaining what are the basics of an SPR and how an SPR system works. So today I will show a few of the applications of the SPR, especially how SPR is used in biosensing, as well as I will touch one of the works that we are working here on SPR imaging, and then I will give a brief introduction about machine learning, how we use machine learning for our sensing purpose. Yeah. Okay. So to start with, I will start explaining what is a biosensor, and then slowly move to SPR biosensors and how to enhance the signal in SPR sensing, as well as the SPR imaging, then machine learning. Right. So initially, to start with the biosensors, when someone asks you to define a biosensor, so it we have to define three important parts here. One is the bioreceptor, where you have your cell, DNA, or a protein, or any kind of a biological molecule which acts as a bioreceptor. And then you have a transducer. So a transducer is the one that converts your biological or a chemical reaction into a measurable signal, which can be an optical, electrochemical, piezoelectric, or a thermal based transducer. Then you have a signal output which just displays your signal. So all these three components combined together forms a biosensor. Especially the most important part is the transducer. So the transducer can be a different techniques, which can be a simple optical technique, or it can be more sophisticated piezoelectric technique. It depends upon the application of your interest and the sensitivity that you will be needing for your biosensing purpose. So the first component of a biosensor is the biorecognition element, or the bioreceptor. So the most widely used bioreceptor are two things. One is nucleic acid material or your protein molecule. So what brings the specificity for these nucleic acid or the protein molecules is, in concern with the nucleic acid, we know the nucleic acids can be classified into DNA and RNA. So DNA is in double helical structures which are combined together through hydrogen bonds. Here, the specificity comes with base pairing. So, for example, these are the four different bases: adenine, thionine, thymine, guanine, and cytosine. So, there always exists and specificity. For example, A always pairs with T, and C always pairs with G. So, this kind of a specificity is not changing at any time. So, that's why the nucleic acid material are used as an biorecognition element, given that it is more specific, the interaction is more specific, and it can be controlled. In case of protein molecules, we have to start with what is a protein molecule. So protein molecule, simply when we say, it is a chain of amino acid residues. So we have 20 different amino acids in our body. All these 20 different amino acids, they combine together by a peptide bond to form an amino acid chain. This amino acid chain further undergoes structural modifications like secondary structure and tertiary structures. So the secondary structures are beta sheets and alpha helix. Then these structures further confine to form a three-dimensional structure. The tertiary structure of protein is known to be the active protein structure. So remaining the primary structure and secondary structure, the protein doesn't have any activity. However, when they form a tertiary structure by folding, it forms something called active sites, to which a particular substrate can go and bind. So it's like a lock and a key. So you have a lock which is on the protein, which creates a lock by the three-dimensional folding. And then you have a key which is a substrate which can specifically go and bind to this region. This is how protein can be used as a biorecognition element. So now the thing that you have to understand is, when you talk about biorecognition element, the most important part is your selectivity. How selective your the biorecognition element is, where either it can be a protein molecule or a nucleic acid molecule. So these are some of the conventional sensors that are available in the market. So one is the pregnancy test kit, which is well known, which is an optical based technique, and you have aquacheck, which is an electrochemical based technique. Here we will see more in detail about the SPR and then the SPR, how the SPR works. So this is the simplest diagram that you can see in the internet, and this contains a light source and a detector, which I was explaining last 2 days before how this mechanism works. So simply, if you put some molecule on top of this, this molecule creates an effective refractive index change on the thin layer of gold, which can be detected as a peak shift. So what usually people do is they just put at a particular angle or a particular wavelength, and then see over time what is changing in this particular wavelength. Because of this peak shift, you see there is an increase in the response, which is here. So this is the association of the biomolecules that is coming, and then after some time it creates an equilibrium. Then the molecules dissociate to form an thermal equilibrium within the system. So this is how the SPR system or an SPR mechanism works, where you put the SPR at a particular angle in case of an angular interrogation, or at a particular wavelength in case of wavelength interrogation, and then see what happens at that particular angle, the reflected intensity. What brings the significance for this SPR system is, so the SPR system is an label-free detection system where you doesn't require any labels. You just put your molecules and then the molecules interact on the surface, which can be analyzed. And this is one of the technique where you can see the real-time molecular interactions. For example, if I have a protein and an analyte, if I wanted to see how this protein and the analyte molecules are going to interact and what is their binding affinity, then I can use this SPR system, where the SPR system can give a real-time readout of this molecular interaction which is taking place on the surface. And the molecular interactions are very sensitive to picomolar down to femtomolar concentrations. Given its high sensitivity, it is applied in wide applications like disease diagnostics, drug discovery. For example, if I have an analyte and then I wanted to, if I have a protein and then I wanted to see hundreds of drugs and then see which drug is going to bind effectively, then I can use all these 100 drugs and then see how this binding interaction taking place, and then I will be able to know which drug has a high binding affinity, and then I will select that drug. So that's how it can be applied in wide range of applications. Then it can applied for wide. It is more versatile in the sense we can detect protein-protein interaction, nucleic acid hybridization, as well as an enzyme substrate interaction, antigen antibody. So any kind of an interaction, biomolecular interaction, we will be able to clearly identify what kind of an interaction it is and what is the binding affinity using the SPR system. So all these things contribute to the very sensitive nature of the gold film that is on the top, which is very sensitive to the refractive index that is happening to the surrounding medium. The other things are very common, which is like a minimal sample requirements, high throughput capability, and ease of use. However, the most important things are real-time monitoring of molecular interactions to identify the binding affinity, which can be identified down to picomolar to femtomolar concentrations. So these are some of the enhancements that people are doing to further increase the signal. So here, for example, if you have very few analytes coming and binding to your sensor surface, then the refractive index change. For example, if this three molecules are the analyte, so the refractive index change that these three molecules creates are very negligible. In order to amplify this signal, what people have done is they go for an labeled assay. So as such, SPR is a label-free sensing. You don't require a label. But however, in case if you wanted to increase the sensitivity, for example, previously I mentioned it can detect from picomolar to femtomolar concentration. But if you wanted to increase the sensitivity to attomolar or sub-attomolar concentrations, then you have to use a label to enhance the signal. For example, you can use in this paper they have used gold as a label, and because the gold, and here you have a gold thin film which expresses the SPR nature, and you have a gold nanoparticle which expresses an LSPR, localized surface plasmon resonance nature. And once it is kept near to your SPR substrate, then there will be an resonance coupling that occurs. Because of this resonance coupling, you see the signal is significantly enhanced. So, for example, when they put your analyte molecule, so this is your analyte molecule which just binds the secondary antibody that just binds here, and here your signal saturates, for example, at zero point 0.7. So the shift that you can see is just zero point 0.7 nanometers because of these two antibody that is binding. But if I put a nanoparticle on the top and then enhance the signal, so from zero point 0.7 you are enhancing the signal up to 7.5 nanometers. So this is the signal that can be enhanced. So at least a 3 times enhancement in the signal can be obtained using a label. Example, a gold nanoparticle label. And in this paper, they have also studied how different sizes of nanoparticle can be used to enhance the sensitivity. So when you use a smaller size of nanoparticle, it had a low LSPR property, and then the resonance coupling will be significantly less. That's why your signal is like kind of a 5 nanometer shift or a 10 nanometer shift. But however, when you use a larger nanoparticle, for example, 33 nanometers, which is used here, as well as 52 nanometers, then you see a significant change in the response. So this is one way you can increase the SPR signal from zero point 0.7 units to 3 times that of your signal that we are obtaining with a simple molecular interaction. And the second method of enhancement is material stack, where you can put different materials on top of the SPR film. For example, here instead of gold, they have used silver, which is more sensitive than gold. Then they used ferrous oxide, graphene. So all these material stacks are going to improve your effective refractive index on the silver surface. Further, when you're going to modify this refractive index by introducing a biological molecule, it will enhance the sensitivity of the SPR system. So there are two methods of enhancement. One is using a label and the other one is using a material stack. So either you can use a single material, bimaterial, tri-material. So it depends upon the application and what is the intended use of this platform. Here they use this for COVID sensing, and here you can have the table where they have used like graphene, simply graphene without any additional layers. They simply used graphene, and then they could get a sensitivity of 121.67 degrees per RIU. However, when they use this ferrous oxide and then graphene together, a bimaterial, then they can achieve a sensitivity of 293.8 degrees per RIU. So it completely depends upon what is the material that you put, what is the refractive index change that it can create, and what is the specific interaction. So depending on this, you will be able to achieve a better sensitivity. Now, I will talk about this multiplexed analysis using SPR system. So in the previous case, we are talking about only one analyte, either a COVID molecule or an CEA protein. But however, people are more interested in multiplexed analysis. When we talk about multiplexed analysis, here we can define this multiplexed analysis in two ways. One is you wanted to detect multiple analyte in your sample, or you do multiple assays on a sample, so on a sensor surface. So the multiplexed analysis can be defined either multi-analyte analysis or multi-sample analysis. So the existing technologies like RT-PCR and ELISA multi-sample assays are available in the market to do such kind of an assay. For example, this RT-PCR was highly helpful when the COVID outbreak came, so that they can analyze multiple samples at a single run. Here, what we are working on is we are working on a very sensitive platform, which we wanted to make as an alternative to the existing RT-PCR based assays. Here we wanted to make the SPR platform into an imaging platform by introducing pico wells. Like you have a gold, and then on top of the gold I put a polymer and then open different channels. So now each of the channels acts as a separate SPR sensor, and you will be able to do a multiplexed analysis. In combination with this platform, we also wanted to introduce a novel amplification strategy. So in case of an RT-PCR, the RT-PCR works on exponential growth of or an exponential multiplication of your DNA. So if you take a single DNA at the end of your first cycle of PCR, you will get two DNAs. So from 1 to 2, and this 2 again goes and divides like 2 power 4, and then it goes to 2 power 5. Like this you will get different number of copies. So this is n conventional rt pcr and how this rt pcr works. But one of the disadvantage with RT-PCR is it always requires a temperature cycle, which has to be very sensitive, because since you use different protein molecules, and these protein molecules are very sensitive to the temperatures, maintaining such an precise temperature and using this thermal cycling is always a challenge when you use this RT-PCR. So people are trying to come up with an isothermal based amplification, and one of this isothermal amplification that we work on is this rolling circle amplification. So when we take a DNA from an E. coli or some of the primitive bacteria, the bacterial E. coli replicates in this fashion. It has an original DNA molecule which is a plasmid, and then it replicates by creating a replication fork, which then divides, and then later it just separates into a two different DNA molecules. So this is how this rolling circle amplification works, where one DNA is just formed by forming a replication fork. It can divide into a two DNA segments. We took this as an example, and then we wanted to establish an assay using this rolling circle amplification. So where you take a DNA molecule and then you design a padlock probe, which is called a circular DNA template. This circular DNA template goes and attaches with your linear DNA molecule. Then you put certain enzymes to replicate this DNA in a circular fashion. So after some time, it just replicates, and then form a bulk of DNA, which can be analyzed as different spots here. So we wanted to combine this along with the SPR platform that we are building. So this is how we wanted to make this ISPR platform, where you have a light source. Instead of a detector, you put a camera. So here you see when I increase the refractive index of the medium here on the top, then your SPR peak shift. Here what we did is we put this at a particular angle and then see what is the amount of light reflected using a camera. So it is just simply a contrast based measurement. So if I'm going to see at this angle, so I'm putting the detector at this angle. If my refractive index is 1.33 on the surrounding medium, then the reflected that I have is zero, because there is no light reflecting, all the light is getting absorbed. But if I'm going to create a refractive index change, for example, if I'm working with 1.344, then if I cross this line, it just binds here, and then you see that the reflection increased. Now it is not a zero reflection. However, the reflection increase and your contrast is different. This is how when you increase the refractive index and then you measure the contrast, your contrast is going to increase over time, and then at some point you are going to get a brighter surface where all your light is reflecting, like here almost all your light is reflecting, and then it is no more darker. So this is how you can create a local refractive index change and then measure the contrast that this refractive index change creating. This forms the basis for the ISPR or a multiplexed ISPR system that we are building here. And the assay that I have mentioned before, the rolling circle amplification, this is how it works. And here by putting a different target molecules, a different target DNA molecule, you will be able to amplify each of these wells and then detect each of these wells using the machine learning platform. So all this process of making the gold chip, making the wells, all the structures are made here in our clean room. So the first step is to create the SPR chip. So simply you take a glass wafer. On to top of this glass wafer we have to coat gold. But our gold is not very sticky, so we have to use titanium or chromium as an adhesive layer to form gold on top of this. So usually what we do is we take the glass wafer. On top of the glass wafer, we put 5 nanometers of titanium or chromium, and then we put 45 nanometers of gold. Then we take this wafer, dice it into small chips, and these chips are then characterized for their RI sensitivity to know what is the RI sensitivity that we are getting. So then we will evaluate what is the RI sensitivity change that we are obtaining with all these chips and then calculate what is the percentage deviation. So these are the initial experiments that we have to do whenever we have to establish an SPR platform. Then we use lithography, UV lithography process to make these wells. So initially you have a glass chip coated with 5 nanometer titanium and 45 nanometer of gold. Then on top of this we coat a polymer like pyrrolizine or polyimide. Then we coat a photoresist on top of this. Then we create these structures using a mask using lithography. Then the structures are opened using etching. So once the structures are etched, then we'll just remove this photoresist on the top. Then we create an ISPR platform with such nanovolts or microvolts, which has picoliters of volume to act as a sample surface. Then I was talking about the SPR system, and we wanted to convert this into an SPR imaging. So previously, you have just seen a graphical representation of how an SPR system is there. So you simply have a prism, and then I just showed a glass chip and mentioned there is a light source and a photodetector. But this is how your usual SPR system looks like, a research-based SPR system looks like. And here, what you can see is the laser, which acts as a light source, and then we have mirrors that can focus the laser light towards an optical focusing lens. And this is the platform where you have a prism. So then the light goes and hits the prism, then gets reflected and goes to the camera here. And here the thing is you can rotate the stage as well as the camera to any angle of interest that you want. So initially this is the image that we got, but here you can see a lot of fringes that is happening because of this focusing lens. So especially when you convert an SPR system into an imaging based SPR system, you wanted to remove all these freckle patterns. These freckle patterns are removed by using a diffuser lens instead of this focusing lens. So we just put a diffuser plate which rotates in anti-parallel direction. So when the diffuser lens rotates in anti-parallel direction, it creates a local path difference that makes the image free from this speckle patterns. So this is how the imaging SPR is built, and here you put your sample, and then the whatever the reflected light you can image here using this camera. And you have several simulation platforms, like one is Lumerical, and using Lumerical you can simulate how these wells are made, and how when I put light to this wells, how this wells will react when I create a local refractive index change and put it at different angles. What will be my RA sensitivity? All these things can be simulated using this Lumerical platform. That's what we usually do when we establish such kind of an assay. And here you can see, so these are the wells which are imaged on this kind of a setup that I have showed you. And this is the amplification that which is done on each of these wells. And you can see that it is darker when it is started, and once the amplification is done and you created a refractive index change, it transferred from darker region to one brighter region. So here you can see how the mean pixel intensity goes up. So this is how the IE-SPR or a multiplexed imaging SPR can be established and realized for a particular kind of an assay. So here I have shown you an amplification of DNA molecule. Instead, you can simply use a protein-protein interaction or a protein small molecule interaction of whatever your interest is. However, the challenge is how to get these wells and how to detect this in the real time. So, in case of a single sample, it is much easier. So you just see how it happens at the real time by just putting at an angle. But here you wanted to identify each of these wells and then try to get what is the response that you are getting from each of these wells. So in order to achieve that, you use the machine learning platform, especially TensorFlow, to identify these wells and then measure the contrast that is getting changed. So to give a brief on the machine learning and the artificial intelligence that we can employ here. So when I talk about artificial intelligence, so artificial intelligence is a bigger platform that makes the mission to do or that transfers the intelligence of a human to a mission. So that's how the artificial intelligence works. So machine learning and deep learning are some of the subsets of the artificial intelligence where deep learning requires a lot of data, a huge number of data, and it can process such huge number of data. But machine learning may not be able to perform a huge number of data, but it also can predict few of the structures like what we have here. To go in deep to make you what is the difference between a machine learning and then deep learning. In case of machine learning, you always record and structured data. So for example, the images that I have shown here, so these kinds of images. So for a machine learning purpose, I wanted all these images at a specific size. So the wells have to be specifically at that particular position. There should not be a change in the position at the uniform contrast of the background. So all these things I have to take care when I do machine learning. But however, for deep learning, this is not concerned. I can just randomly take a lot of images like this at different contrast, at different well sizes, and then the deep learning can able to perform the function. So that's the major difference between a machine learning and a deep learning. Then, as I was mentioning, the deep learning can do this complex algorithms, but machine learning cannot perform complex algorithm. For feature extractions like what we wanted here, we wanted to use deep learning algorithms, but initially we will start with the machine learning and then go in depth with a lot of images to achieve this deep learning platform. As per the performance is concerned, your deep learning always outperforms machine learning because deep learning has a lot of data inputs rather than that of the machine learning. So how the deep learning works? In a simple example, I will tell you how this works. So you have this biological neuron, right? And the deep learning always takes this neural network as an example, and then try to make a similar computational coordinates which replicates the functions of a biological neuron. So when you take a biological neuron, so the biological neuron has a dendrites, so where you put the inputs or the stimulus is given, and then it transfers to the axon, and then this axon just transfers the information to the next neural cell, or here we consider as an output. So here the input that we consider, and then there is a neuron where you perform a mathematical task and then you create an output. So this is how the biological neuron and an artificial neuron is connected for deep learning purpose. For example, the dendrites that we consider here is considered as an input in case of machine learning, and then the nucleus of the cells are the nodes which is created from your input signal that you are getting, and then your synapse is the weightage that you are giving, then the axon is your output. So this is how the neural network is connected to your artificial neural network. For example, the first step that you have to do is, I will go to this slide and then we'll come back. So for example, in your class, You just randomly give a paper to everyone and then ask them to write a letter E in the paper. And then you wanted to create a machine learning platform or a deep learning platform to identify this letter E from a large number of data. For example, if then the mission you are going to train your platform in a way that whoever writes the letter E in whatever format, it will identify, okay, this is letter E. How it can be done. For example, you have to create this letter E, and then you have to create an input first. To create an input first, what the machine learning does is, so from all the papers that you have written E, it creates a small pixels, and each of those pixel now act as an input. So for example, here you have a pixel of 0, 0, 0, 0. So all this 0 or all this number now act as an pixel. So these pixels now act as an input. So this is the input that you are getting, and this input is multiplied with then random numbers for that is the weight 1, weight 2, and weight 3. So here you can create random numbers like point 0.1, point 0.2, point 0.3, and then create a net input function. So you have an input and then you add a weight to the input and then create a net input function, which is called as bias. So the first step of machine learning or a deep learning is to create a bias where you put an input, create an input, put a weightage to it, create a net input function, and then create a bias. And then the second step is all the weights that you have created to the inputs have to be summed up, and this sum has to create an activation function, or you have to define a threshold. For example, if we go here, so if I'm going to take this paper and then segment it into different pixels and then give a different values to this. So for example, if I take the first input and then I multiply it with a weight, for example 0, 1, and then it gives me an output, right? So if I'm going to create uh, all these pixels with zero point 0.1, multiply all these pixels with zero point 0.1, then I will create an input, create a net input function. That net input function should give me a threshold. So here I can create a threshold. Okay, whatever happens, if I'm going to have the threshold by giving a weightage, if I'm going to get the sum of 50, assume 50 is your threshold, whatever comes above 50, then it create an output of 1, or the neuron is fired. If I'm getting a value less than 50, then the system assumes it is not an function. Then it will create an output as 0, or the neuron will not fire, right? So okay, so this is how you create a net input function. Then you create this output by adding all the weights that you have considered, and then the input value plus your bias. Then you define a threshold. Either this threshold can be a simple number of 50 or 20 or 30, whatever number you decide. You just give this threshold to it, and then it create an output depending upon the threshold you give. So it creates an output of 0 if the summation that you are doing is less than that of the threshold that you have defined. It will create an output of 0, which says the neuron is not fired. And if the summation is more than that of the threshold that you have defined, then the artificial intelligence consider it as an correct input and then fires the neuron, or it gives an output of 1. So this is how a simple deep learning can be trained by using a large set of data. I've just taken one of the paper and created a small pixels. Like this, for example, if there are 50 people in your class, you have 50 papers, and then all these 50 papers are subdivided into different pixels. Then you put weightage to all these pixels and then create or train your machine learning to create an activation function, which is the threshold. So once the threshold is defined, then the then the neural network is trained to give an output as 0 or an 1. So this is how the A simple deep learning can be trained and to give an output. To do several functions within the machine learning, for example, here I just try to identify a number. So this is just an identification platform. In the SPR imaging case, it has to recognize a particular region within the sample that I am giving or within the input that I am giving. So it is called recognition. So for doing different functions for classification, or you do a regression or clustering, so for different functions you have different algorithms that the machine learning works. So one of the simplest algorithm that you can see in the internet or you can try to do on your own is the classification. You simply take the images of an apple, tomato, or any kind of an vegetables. You just take 10 such image and try to do a TensorFlow platform, and then train the platform to identify Apple at all the time. So once you train the platform to identify Apple, then wherever, whatever the images that you put, if that image has an apple in the figure, then the machine learning could identify, okay, this image as an apple. So this is how you can simply train. And I would suggest you all can do the TensorFlow platform, which is free to use in the internet, and there you have the algorithm already written. You have to just learn it and then try to give a lot of inputs, a lot of training to the platform, and then you can learn how we can do an machine learning or for different applications. Okay. And this is for today, and here you see IW1 and the members of IW1. And in case of openings, we have two master thesis openings. We are DAT fellowship, so if anyone is interested in applying for DAT fellowship, you can contact me. Also, there is a one exchange PhD fellowship available, but this is quite tricky because an MOU has to be signed between the institutes. So this may not be useful. But however, master thesis, if someone is doing your MTech, you can and interested in doing SPR and such kind of an bioassays that I'm talking about, or the machine learning platforms, then you can write an email to me, or you can mention it to your Professor Alvin, and he will let me know. Then we can do the needful. Okay, thank you. Any questions? Okay, thank you. Yeah, see you.